Today we're going to be taking a high-level look at the MetalX system from Markforged. So just as a kind of a quick outline for our agenda today, we'll first be taking a simplified look at each part of the atomic diffusion additive manufacturing process, which is the process that Markforged uses to create 3D printed metal parts. Just for the sake of simplicity for the rest of the webinar, we'll refer to that process as ATOM. Once we get a sense for what ATOM is, we'll take a bit of a deeper dive into the overall process of how the MetalX creates parts from the software start side of things all the way to the end. Think of this as a bit of a more detailed look as to what goes into each step of printing a metal part. After we take a look at the how portion of the MetalX, we'll focus more on the kind of the why of 3D metal printing. To do that, we'll take a look at some of the advantages of ATOM, and we also have two quick customer case studies to show you just as examples of what can be done with the MetalX. Once we get near the end of our webinar, we'll take a look at some of the recent additions to the MetalX, and we'll also take a look at some of the upcoming materials that you can look forward to using. And of course, it wouldn't be a webinar without a Q&A section, so we'll hopefully be able to address some of your unanswered questions at the end. So with that being said, let's go ahead and get started. All right, so what is the ATOM process? Like with most modern manufacturing methods, you'll first be working with your CAD software to design your part or assembly. Once you have your design, you'll export an STL file from that software and upload it to the Markforged Eiger software. Since Eiger accepts STLs, you'll be able to continue using your CAD software of choice for the actual designing portion. Eiger is also really simple to use and lets you customize how your part will be printed. When your part is fully uploaded to Eiger, you're able to very easily forward it to your MetalX for printing. The material that creates your part is a filament strand that's made up of metal powder bound in wax and plastic. If you're familiar with the layer-by-layer printing process of other Markforged printers or any other extrusion-based machine, the process here is nearly identical. Now, if you're reading the print display card here, you may be seeing the note about scaling and shrinking. We'll go over why parts shrink during the ATOM process in the next few slides, but because the shrinkage does occur, Eiger scales parts automatically to account for that shrinkage rate. The rate itself is about 20%. Since the Eiger software scales your parts without any needed input, all you or your designers have to worry about is designing your parts with their intended dimensions. Once your part is actually printed, it's referred to as a green state part. Green parts need to have some of that binder that I mentioned removed before they're able to be finalized, so they're washed in a liquid called Opteon SF79 to accomplish that. When a part has been washed, it moves to what's called the brown state and is ready to be sintered. Sintering will fuse the remaining metal powder together, and once that's done, you have your final part. After the sintering process, parts are fully complete. If you want, you can post-process them with pretty much any method that would be compatible with the underlying metal itself. So things such as shot peen, heat treating, anything you can kind of think of in that regard. Now, for those of you that are in a manufacturing-related industry, if that overview sounded familiar at all, it's because Markforged designed the entire ATOM process around the concept of metal injection molding. I've included a bit of a flow chart here that it shows a typical metal injection molding process, and you can really see the similarities to what I just described. Metal injection molding has been around for over 40 years now and has many uses in manufacturing, so the process isn't exactly a new concept. So while metal injection molding has been around and is extremely reliable and useful, it's typically only used for high volume production, and it's not usually accessible or affordable. So what Markforged did is they took that existing concept, scaled it, and used their knowledge that they have in their composite side of 3D printing to refine it into the MetalX system that you see here. So now that we have kind of a baseline understanding of what ATOM is, let's run through the process of creating a 3D metal part. As I mentioned earlier, that process all starts with the software, which for this webinar today, we'll start with the Markforged Eiger software. Eiger is an easy-to-use cloud-based solution that is based off of Google Chrome. That means that as long as you have Chrome installed on your machine, you don't have to worry about installing or updating additional software, since updates to Eiger are automatically applied. Now, since Eiger is based in Google Chrome, That also means that you can log into your account from anywhere that has access to that browser, which lets you see things like your printer status and remaining material remotely. Now, a big part of remotely managing your printers is being notified of any updates to your prints or printer status, which Eiger lets you enable via email if you want to. Lastly, Eiger lets you create organizations for multiple users, so anyone that is invited to your organization can help manage your printers, your part library, send parts to the printer, things like that. So for anyone who hasn't had a chance to use Eiger before or seen a demo of it, we put together a quick video here to show just kind of how easy it is to start a print with Eiger. As I said in my previous slide, it all starts with uploading an STL to your Eiger library, which we'll do here right now. Once your part has been imported, you are taken to what's called the part view, where you can see your part geometry. Navigating around the part view is super easy and typical of any software. I'm just clicking the left mouse button to navigate around, and you can do things like zoom in and out with the mouse wheel. Pretty standard stuff. Once your part is here, you can select what type of material you want to print with. For this demo, we're changing this to stainless steel. Now, by mousing over this part, you can kind of see that some of the surfaces are highlighting in blue. If we click on one of those surfaces, it aligns that plane directly to the print bed. This makes orienting parts super simple, although we do have more precise control with the manual rotation feature over here to the right, where we can enable a gizmo and use that, or input specific degrees if we want to do it that way. With metal parts, we also have control of the scaling, import units, and layer height. So once you've played with those settings and have your desired settings, you can click Save, which will automatically slice the part and generate the printer toolpath, printer supports, anything that's needed for a successful print. We kept the slicing in real time just to kind of show you how quick it is and how kind of painless it is for you guys. If any of you guys want to actually upload your part to Eiger and just take a look at how easy it is, Eiger is a free trial that you can use. Just feel free to search it and actually create an account, and you can upload your parts. When the part is fully sliced, you're able to see print details like how much material it will use, what the cost of that material might be, and what the print time is. And that kind of stuff is available even without a printer. So right now, the part would technically be completely ready to print, but if you want, you can take a look at the internal view, which we're accessing here, to get a better look of how the part will print. This comes in kind of two forms. First, the overall transparent view, where you can kind of see the whole part geometry, or a 2D layer by layer view, which we can use to see how the toolpath of each individual layer will be printed. We can also click Print from here, which we'll do. And that'll take us to the final preparation screen, where you can add more parts, select your printer if you have multiple printers, and save your build if you want to save that build for a future print. Our printer was busy at the time of this demo, but if it wasn't, we could simply select that printer and click on Print, and that would be able to forward it to the printer. Since we actually saved this part, though, we can go back to our library at any point and print it easily if we wanted to. So just as kind of a quick overview, even with taking our time to go over some of the features, that took less than 3 minutes to import a part and get it ready for printing. So like I said, it's a really, really easy software to use. All right, so we've gone over kind of what Eiger is and what it can do. So let's move on to how the printer actually creates a part that is sent to it from Eiger. Like I mentioned earlier, the MetalX creates parts by using a filament strand based off of metal powder, polymer, and wax. The parts are built from the print bed, layer by layer, up in the Z direction until they're finished. And in this picture, you can see the metal spool is on the left-hand side. Now, speaking of that picture, you can see on the right-hand side, there is another spool, which Markforged MetalX does use as another material. This is the ceramic material that is used to separate support structures from actual part geometry. So what I mean by that is, if you have a feature that is directly overhanging the print bed, the first layer of that feature wouldn't be able to necessarily print in thin air, so the MetalX would create a support structure out of the metal filament to hold it up. The structure and feature are separated by that ceramic release material, which is powderized during the final sintering stage, which we'll go over. This prevents the metal supports from fusing to your geometry, So there's no need for wire EDM or any other sort of post-processing method to remove your supports from geometry. The setup and use of the Metal X is also extremely similar to that of the other Markforged systems. So if you've ever operated a Markforged printer or any other extrusion-based systems, you'll already have at least a basic understanding of how the Metal X operates. So for anyone not familiar with any sort of extrusion-based technology, here's a quick demonstration of how the Metal X builds parts. You can kind of see the white ceramic release material, which is separating some support structures from really deep overhanging geometry. And just to make sure we're all on the same page, this isn't actually how fast the print takes place. It's just a time-lapse video. All right, so at this point, after the Metal X is printed, we have a completed green state part. This particular green state part is just an example of a bottle opener that one of the Hawker Systems AEs designed. The wide feature you can kind of see under the bottle opener geometry itself is known as the raft, which prints under each Metal X part. The raft identifies what type of metal the part was printed with, but during the sintering stage, it also helps to shrink the part in a more uniform manner, meaning that your geometry comes out accurately. The feature on the right-hand side of this bottle opener is another good example of how the ceramic release barrier will support structures from fusing with normal parts. Again, green parts are composed of powdered metal, wax, and polymer. In this stage, they have a consistency of about a tough clay, so they're fairly fragile, and here's kind of a simple illustration of what a green part might look like at the molecular level. When you have your green parts, it's time to move on to the washing stage of Atom. As I brought up in an earlier slide, green parts are washed in Opteon SF79, which is essentially an industrial debinding fluid. The goal here is for a large portion of those binding agents to be removed so that they don't interfere with the sintering process. You may have seen in that earlier Eiger video that Eiger will recommend wash times for each of your parts, so you'll know, in general, how long you need to wash your parts for. Now, obviously, that works for a single part, but what about multiple parts? Well, a cool thing about the wash solution that Markforged uses is that the parts cannot be overwashed. So if you were to, say, start a wash cycle on a late Friday afternoon, you wouldn't need to come in on a weekend to ensure that those parts get removed. The parts will not dissolve. When those parts are completely washed and ready for sintering, they enter what's called the brown state. Brown state parts are a bit more fragile than they were in the green state, but not to the point where they will fall apart with normal handling. On a molecular level, brown parts would look something like this. A very large portion of the binder has been washed out, but some still remains to hold that metal powder together. So when you've printed and washed your parts, the only thing left to do is sinter them. The main points of the sintering process are to burn out any remaining ceramic release material and binder, while also fusing together the remaining metal powder. One of the biggest positives of the Markforged sinter oven is that the sinter time profile is always the same, regardless of how many parts there are or how big they are. So as long as the parts can actually fit in the sinter, you will know exactly when they will finish, both by looking at the sinter UI and monitoring the sinter via Eiger. Here's a real quick example of what is happening during sintering at a molecular level. So as you can kind of see, the remaining metal powder is fused and pulled together, resulting in your design geometry. The raft that I mentioned earlier, again, helps to more accurately pull part geometry together as a whole, rather than each feature shrinking at an independent rate. Again, the shrinkage is accounted for by the Eiger software, so you don't need to worry about finding out exactly what the shrinkage rate will be. You just design your parts as they need to be designed. When your parts are completely centered, all that's left to do is pull them out of the oven. It's kind of hard to see, but the UI in the left-hand picture will tell you exactly when it is safe to do so, so there's no guesswork here. As a quick example, here is a finalized version of the mini motor mount that we uploaded during our Eiger demonstration. Markforged put this video together to show a quick example of what removing a part from the raft might look like. So when parts are pulled out of the sintering oven, you can immediately put them to use if you want. In terms of actual material properties, you can expect the metal itself to be up to 99.7% dense, while also having properties similar to wrought machined parts of the same metal. We won't go into too many details about materials today, but the data sheets on each available metal material are on the Markforged area of our Hawkridge system website, so feel free to take a look. Now, again, because they have similar properties as machine parts, Markforged atom parts can be post-processed in any way that would be applicable to the base metal. I mentioned a few examples earlier, but any further machining action that you want can also be done. As an added benefit, Markforged parts print with an infill pattern, making them lighter when compared to other similar parts. Infill like this would be impossible to produce with a powder-based or CNC solution. So we've gone over the basics of how Markforged is able to create metal parts, but what do you stand to gain from using the MetalX? Well, as we've already gone over, the atom process is a scaled-down version of existing techniques. So as a manufacturing method, it's already been proven to work. There's no theory crafting, no guesswork, which is a huge positive. If you compare it to some of the other 3D metal printing methods, it's not only safer and cheaper, but it's much easier to use. As an example, DMLS solutions, as you can see here, require quite a bit of safety gear, while also requiring a highly trained individual and a much larger initial investment. The Markforged Metal X is extremely straightforward and safe to the point where the Markforged print farm is operated by a single person who isn't a trained engineer. Like we showed in the last slide, infill patterns can be created with the Metal X, leading to lighter parts that use less material. So if you were pushing a material to its limits, a solid part may be theoretically stronger, but a huge portion of applications don't really require a solid part. So the added benefits when compared to the time and money investments are not usually worth it. So even though the solution as a whole is scaled down, the Eiger software lets you run multiple printers or sinters in parallel, letting you scale your production as much as you want. The Markforged print farm that I just mentioned, the one that's only operated by a single person, consists of several dozen printers, both from the composite and metal side of things, and Eiger lets them all be managed easily and remotely if needed. Then, of course, there are the benefits of simply removing the lead time and production costs associated with sending a part out to a machine shop. The time-saving potential is really, really big, especially in low-volume requests, which typically tend to get backlogged due to priority. Instead of waiting weeks for a part to get machined and sent back to you, the part could be in your hand within a few days. This lets you obviously test and iterate more because you don't have to wait for your part to be manufactured at a shop again after a simple change. Now, all of those benefits don't really mean anything if the printer can't create parts that are accurate and do that reliably over multiple runs. So just like with their composite machines, the Metal X is able to do both of those things easily. For an example, let's take a quick look at these example metal ball joints. Each of these two components, so the top and bottom, are printed on separate Metal X systems and are able to thread together with absolutely no post-processing other than a bit of lapping compound on the threads. Markforged uses these as demo pieces, so as you can imagine, for a company that has a global footprint, quite a few of these are printed at a fairly consistent rate. For accuracy itself, you can obviously expect to get near net shape with parts printed on the Metal X. Tolerances typically range about plus or minus 125 microns, which in Imperial is about 5 thou. Though Markforged does get accuracy in some parts down to 2 thou. Now, just like with all manufacturing methods, right, Atom has applications that are better fits for the technology and applications that aren't. So here are some good examples of geometry and applications that are well suited for the Atom process. So this is going to be hardware such as jigs, fixtures, jaws, and anything else that is typically associated with lower volume and high lead times. These are all excellent candidates. Again, with quick turnaround times, you're obviously able to iterate and test these designs more than you normally would. You can also print as few or many as you want, rather than ordering a lot from a machine shop to drive the cost down. This obviously has the added benefit of inventory management. Now, what the Metal X will not do is replace components that are easily available off the shelf. This is stuff like sheet metal brackets, bolts, nuts, or dowel pins. Now, as you saw in the last slide, this doesn't necessarily mean that the Metal X can't create these things, so it obviously can print threads, as you saw, but anything small that can be bought cheaply and in really large amounts from your local hardware store, it's simply not a good fit for the technology. Okay, so it's usually helpful to see some real-world examples of the technology in use. So let's take a look at a few case studies that Markforged has helped with. The first one will be for a Metal-X printed hydraulic actuator housing that is used by Stanley Black & Decker. The silver component on the left-hand side of this slide is the printed component itself. Let's take a bit of a detour and first define what this part is and what it does. So on the left-hand side, you'll see the pulse toll driver that the actuator is a part of. Pictured in blue on the right, the housing actuator transfers trigger pull forces through a group of ball bearings. Stanley Black & Decker only needed a few dozen of these per year as replacements, so their choice was either send the order out for only a few at a time, meaning that the lead time would be high, or pre-order them in higher amounts, meaning that they had to use up inventory space to store them. Based on just those two things, this part was already an excellent candidate for the Metal-X. For how this part was made, the actuator housing was originally made up of 4 parts. The component in blue on the left was a cast part, with the reddish component being a laser cut cover. To better take advantage of the Metal-X, engineers at Stanley Black & Decker redesigned the assembly into one part while also modifying the through channels into teardrop and diamond shapes so that they did not need to print with support material. If anyone here keeps up with our blog, you may recognize this as the first part that we printed with our Metal-X system. With cost and time-saving metrics in the 90s for just a single part for Stanley Black & Decker, I think the results kind of speak for themselves. Now, obviously, the part needed to be tested, and Stanley Black & Decker actually had to use methods beyond what they would normally test with to get the part even near a failure state. So because of how well this part performed for them and how much it actually saved them, Stanley currently uses this part in production environments. Now let's move on to our second case study, which is Dixon Valve. Some of you might already be familiar with Dixon Valve and the fact that they already use Markforged composite printers to enhance their capabilities. You can easily see a Markforged printed composite soft jaw and some grippers on the pictures on the right and center of this slide. However, there are just some applications that plastics or composites aren't able to tackle, in this case, such as when they're pressed against sharp threads with high force. This is where the Metal-X came in for Dixon, with the Dixon gripper jaws that we'll take a look at. You can see them in the picture on the left-hand side. Here's a real quick video of the gripper jaws in action. As you can see, the jaws hold a coupling from their inner threads, moving them to an assembly fixture. This particular coupling presses a polymer crush washer, and once the task is complete, the jaws are actually moved from these couplings to a tray for packaging and shipping. A cool note here is that the actual arm is only moving at about 30% speed in this particular video, and safety doors have to be closed when they really get it up to speed. So we've covered what the technology is and some of the things you can do with it. So now let's move on to some recent additions and some upcoming materials as well. So the first thing we'll cover is the recent release of H13 tool steel. Here's some quick pictures of prints done with the H13 material. Because of how hard and tough it is, this type of tool steel is used a lot in tooling such as punches and forming tools, but also things such as injection molds. The really cool thing here is that switching between different materials on the Metal-X is really easy. All you have to do is load your desired filament type, make sure that Eiger has the correct material set, and print your part. So let's cover one of the more exciting new additions, which is the release of the 50 micron layer height alpha test. I think that for this one, pictures are better than words, so let's take a look at a test that was done at 50 micron height. So like you can see here, 50 micron layers really lets you get those finer features to come out nicely. Those of you who are familiar with the industrial series of Markforged composite printers already know that the X series can print onyx at 50 microns, so the ability to do the same with metal is really cool. Last thing we'll cover here is the upcoming materials roadmap. Like I said, H13 tool steel was just released, so along with stainless steel, there are 2 fully available materials. So let's take a look at what you can kind of expect coming forward. An upcoming material on the roadmap is Inconel 625, which is a metal that's usually known for its high chemical and heat resistance. That means it's used fairly often in the aerospace industry. Next on the upcoming materials list are A2 and D2 tool steels. These are hardened and are excellent for things like punches, dies, and forming tools. A2 is usually tougher, while D2 often has a higher abrasion resistance. Next on our materials list here is titanium. This metal is lightweight and has a really high tensile strength, which makes it common for uses in applications like aerospace engines for things like turbine blades. And last on the beta roadmap here is copper. Obviously, this could be characterized by its great conductivity, but it also has good corrosion resistance properties. And that's it for most of the content we had. If you want to see some Metal-X parts in person or want to potentially see some Markforged printers in action, I've listed the locations of where we have full digital manufacturing labs. So we definitely have quite a few locations where printers and parts are available, but obviously we also have offices in quite a few locations across North America, as you can kind of see here. If you have any questions, feel free to take a look at our website for the location and contacts nearest you, and we can help you out.
Our first question, it comes from Jim, and he is asking if the centered parts can be heat treated with proper alloy.
Yes, and in fact, if you look at the data sheets for the two materials that are available, which are 17.4 stainless and H13 tool steel, those are available on our website and the Markforged website. They should have some statistics on the strength of heat-treated parts after they've come out of the sinter oven.
All right, second question is from Eric Albert, and he wanted to know if the support structures stay with the part through sintering.
Yes, yeah, the support structures do stay with the part during the sintering process, but because of that second filament strand, the ceramic release barrier, they don't actually fuse to your geometry. They're very easily separated.
He had a second part to his question in regards to how about hollow and tubular parts?
Essentially, if you have a hollow part, so something where you actually have a cavity designed, if it needs support structures, so if you have something that's directly overhanging the print bed or anything near less than a 45-degree angle, the Markforged printer will put supports just to make sure it doesn't droop. So something like a through channel where you can access that is beneficial. So if you don't have any ability to access that, that would be something where, like Stanley Black & Decker did, you just redesign your channel or cavity to be maybe a diamond shape, a teardrop shape, something like that that doesn't need supports.
Great. Next question is from Jeff Collins. With the ability to print H13 and shortly in beta A2 and D2 tool steel, would it be possible to surface grind a shear edge which would have the strength in the printed block to be used for punching thin wall and aluminum extruders? And he gave a measurement in there, 0.085.
Yeah, so you would be able to machine both of those materials. Typically, as far as grindability, you're going to be usually using A2 versus D2 as far as for that particular material. And as far as grinding or any sort of machining, typically you're able to remove about 0.5 millimeter or so of material before you actually get too close to the infill of the part.
All right, Nicholas Hathaway is asking, can a part be filled with a solid fill?
So at the moment, the only way that you can print a part is with a infill, kind of like I showed earlier. Now, the printer would be obviously capable of printing a solid filled part. In fact, the 50 micron alpha that Markforged is currently testing prints with solid infill. But the things that they kind of have to dial in along with solid parts are how long does that take to wash, because that wash fluid has to infiltrate the part. It has to get that wax out of there. So it's going to go back to that argument of whether or not your application actually needs a solid fill or if a hollow infill would suffice, because a solid fill would take a little bit longer to wash.
Next question from Eric, once again, current materials available? Can you just review that once again?
Yep, so that was 17.4 stainless steel and H13 tool steel.
Next question is from Ron. Does Eiger automatically adjust the scaling factor based on the material?
Yeah, so that's all automatic. Markforged doesn't really release the exact algorithm percentage that it will shrink your part or geometry at. A lot of it is going to be geometry dependent as well. So sharp corners, things like that, will obviously concentrate thermal heat more than other features like fillets. So those would shrink at a different rate. But the software, if needed, will accommodate that all automatically.
Excellent. Next question from Brian Grimm. Are there any issues with welding due to inclusions or contamination?
None that we're aware of. Essentially, the properties that you can expect are close to the machine version out of a solid block. So anything that would be compatible with that, you can do.
Next question's from Dennis. Is aluminum a current or future material option? That question came up a couple
So
times.
everything that I listed on the roadmap is kind of something that Markforged is something that Markforged is currently testing. Aluminum is something that they were looking at, but it's not something that's on their really soon upcoming stuff. But they are obviously aware of people wanting to print in aluminum, so they are looking into that.
Next question from Elliot. Can we design the hollow structure or is it prescribed? Is it less truss structure? Is it like, truss structure?
Yeah, so kind of the same as that question that came up earlier. You can design hollow cavity if you want. Essentially, anything solid in your part would be filled with infill if possible. So if you actually have a designed cavity, that's not going to be filled with infill. It's only going to be filled with support structures if it needs to be supported.
Cool. From Ross, due to the materials parts being somewhat porous, will this be a potential problem if the part is immersed in a corrosive environment? My concern is there is ingress to the center of the meat of this might very well reduce the life cycle of the metal part.
Yeah, so the porosity of a part that actually comes out of the center oven is going to be similar to a casting, so about 2 to 3%. So essentially, it obviously depends on your application, right? And that would be something that we could potentially work with you on to investigate further. Yeah, like I said, it's comparable to other manufacturing methods.
For Matthew, how do the parts work for gas delivery type components? Is porosity an issue for leaking?
I don't think Markforged has helped with any case studies as far as for gas delivery components. Again, as far as porosity, it's going to be about 2 to 3%. So it would kind of depend on what your application is.
Excellent. Also, we have another question in regards to plastic, plastic injection molding, and using this technology.
Yeah, so that could be done. As far as surface finish and everything, if you needed any sort of better surface finish on the part, just to get that mold up enough, you can obviously grind the metal or anything that you need to be done to it after the fact. H13 is really good for injection molds, and it has been used.
On behalf of Hawkridge Systems, we'd like to thank you for joining us today.